Thanks for joining in with us today. Welcome to today's webinar here with us on On24. Here you'll find you can move our presentation space around to your liking, as well as discover a few new features, such as learning about your presenter over there, and being able to contact us offline for any discussions you'd like to have right over here. Jumping into today's topic, ground fault location in PV systems. My name is Michael Fleischer. I'm the digital marketing analyst for Megger, and I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter team. On the left side of your screen, you'll see an ask question window here. And you can submit questions there at any time during the presentation, and I will read those questions out during the Q&A session at the end of our webinar. Additionally, I'd like to remind everyone that a certificate of attendance, copy of the presentation, and link to the recording of the webinar will be sent to all attendees in 2 business days. Our presenter today is Brian Hammerschmidt, Applications Engineer. To assist with the question and answer session, we will also have joining us Felix Lesmes, Applications Specialist, and
Hello.
Michael Palmer, Regional Sales Manager. All right, with that, I'm going to hand things over to our presenter, and thank you for joining in today, Brian. I'm going to pop off the webcam so you can concentrate and not look at this beautiful face.
Yeah, I'm going to go off camera as well. Thanks everyone for joining us today. Again, today we're going to look at ground fault location in PV systems. We'll be taking a look at the importance of doing this testing for ground faults. We're going to look at some connections to earth in PV systems. And then we'll look at some of the common tests that are performed for identifying ground fault locations. And with each of those tests, we'll take a look at the equipment that's used to perform the test. And at the very end, we'll look at just a few additional tests to these typical ones. So why is it important to test for ground faults? Obviously, every electrical installation has to be tested just to make sure it's safe and make sure it's okay to operate. We know that solar plants can produce high DC voltage, up to 1500 volts, and certainly high currents can be present under fault conditions. Quick note on the 1500 volt systems. These were first mentioned in the NEC, the National Electrical Code, back in 2017. And so prior to that, most systems were 1000 volts. But this increase up to 1500 volts, that increase of 500 volts allows contractors to condense systems because each inverter can then process more energy. So you have more panels that can be connected in series to make longer strings. Fewer wires are needed, and then fewer inverters are needed because they can accept more power. Other important things to note for the importance of testing. Any poor or insufficient connections that are connected to ground, these can cause electric shock to people in the surrounding area, can cause a fire. Of course, there's the transmission of lightning-induced surges and presence of electromagnetic interference. And just want to note here, it's really important to use test equipment that's rated to meet IEC and local regulations. Here we have a couple of definitions related to grounding from the NEC. Equipment grounded conductor, or EGC. This is any conductive path that provides a ground fault current path and connects normally non-current carrying metal parts of equipment together and to the system grounded conductor. Grounding electrode conductor, or GEC. This is a conductor that's used to connect the system grounded conductor or the equipment to a grounding electrode or to a point on the grounding electrode system. And then a grounded conductor. This is a system or circuit conductor that is intentionally grounded. So now we're going to look at connections to earth in PV systems, connections to ground. There's 2 basic types. We have floating systems. This is an ungrounded system that connects non-current carrying conductive parts to ground, such as PV module frames and structures. And the other is earth systems, or system grounding. And this is a system that connects a current carrying conductor in the system to ground or earth potential. So we know that these are areas where earth leakage can occur. So here's a diagram of a floating system. This is a floating isolated PV system. A lot of installations will use cables and connectors that are connected to the mains using an inverter with an isolation transformer. So this method permits the array frame to be left floating. And just important to understand that accidental earth leakage can be present from faulty equipment or damaged insulation. But you'll see here, hopefully you can see, these fault current paths that exist in yellow here. So this next diagram is also a floating system. This is a non-isolated PV system. So in a non-isolated system, you'll have additional fault current paths. And these, again, are shown in yellow here. There's various paths. So floating systems require specially rated inverters with array fault detection capability, and they require wiring protection, disconnect devices, overcurrent protection, and ground fault protection. And this is true for both isolated and non-isolated ungrounded systems. This next diagram is a grounded PV system to earth. So a grounded PV system or earth system connects a current carrying conductor in an electrical system to ground or earth potential. So an array output cable or conductor, commonly known as ground, is connected to earth. And in this case, a bonding to ground is made to any of the live DC current conductors. And with this, any planned earth leakage occurs as a consequence of the design of the equipment. Important to note that PV systems by default really should be equipment grounded, and the great majority should also be equipped with a system grounding. So in grounded PV systems, when a ground fault condition is detected by current flow in a grounded conductor and grounding electrode, the circuit is opened and the inverter displays a ground fault alarm. The connection between the grounded conductor and the grounding electrode system is normally made through the ground fault protection device. Just important to note here that lightning strikes can actually also cause damage, either from direct or even a nearby strike, and surges can be induced on the PV array conductors or even the AC cables. So moving on to these common tests that are performed, we have 6 of them here. Visual inspection, continuity and polarity testing, voltage and current testing, insulation resistance or IR testing, and then earth leakage current testing. So we'll start with visual. This may seem obvious, but it's also very important. You want to look for any physical damage to an installation, any modification or degradation of equipment. We know that this equipment, particularly in solar fields, is exposed to environmental conditions, extreme temperatures, dust, corrosion, moisture. Even rodents and nesting animals can cause damage to some of the equipment. So important to check for these things. Here we have some photos. This is just some superficial contamination on a panel. You can see some dirt on there. In this, we're looking at aluminum framing can corrode very quickly, especially if it's near salt water or a manufacturing site. And this can certainly cause problems with conductivity in the path to ground. So checking continuity to ground is really important in these cases. We'll be talking about that in more detail shortly. Here's a photo of some pretty poor condition of cables. Again, exposed to sunlight, temperature, etc. We know that exposure to UV and wide temperature swings can actually cause a premature breakdown of the insulation. It can actually cause it to become brittle in a lot of cases. And you might notice here, we have a bird nest. They decided to build their nest inside the inverter. So this can also cause damage to connections and equipment. That's something to look out for. And here we're looking at bending points in the cable. These are especially prone to shorting to the frame if the insulation is compromised. So this is certainly something we want to pay attention to anywhere where the wires are bent like this. And just a final slide here on this. We have a wasp nest or some kind of bee nest there, and they decided to build it between the frame and the panel there. And here's our last one. We see some UV corrosion. This is a control panel. The screen you can see on this inverter, it's become hazy. It's difficult to read. So this can make seeing a ground fault alarm real difficult. And any indication of insulation degradation, loss in IR, voltage or power, etc., will be difficult to see on a panel that's got this kind of a damage to it. So we'll move on now to continuity testing. In continuity testing, we want to verify that we have good bonding existing between grounding systems, between the PV module frames, structures, conductors, etc. And we need to verify that the earth electrode conductor is continuous, and check certainly the integrity of any of the splices, welds, and other connections. And then continuity of bonding in the metal cable trays, enclosures, frames, fittings, etc. Any components that are serving as equipment grounding conductors. We know that we can lose continuity due to inadequate or damaged mechanical installation. Checking for continuity between the grounded PV array source circuit and output circuit conductors to the earth electrode conductor, especially when equipment's removed for maintenance or replacement. Then here in this photo, we have an aluminum frame, the panel that's joined with a galvanized steel frame. So we know that dissimilar conducting materials can corrode, can lead to corrosion and loss of continuity. Electrolytic corrosion or electrolysis. This can occur when dissimilar metals are in contact in the presence of an electrolyte, such as water, moisture, that contains very small amounts of acid. So again, this is something to look out for and check for continuity in these areas where corrosion can occur. So what is the equipment that we use to check for continuity? Right here, we're going to highlight the Dealer 02. This is the digital low resistance ohmmeter. And we're highlighting this to be used in conjunction with the KCC long test leads. So this allows us to check continuity over long distances to over 300 feet. Note here that the Dealer 0 is also used for other testing, including checking contact resistance of any ground connections, including bus bars. And this unit will put out 2 amps, and it has the ability to read from 1 micro-ohm up to 2,000 ohms. So here's a photo. You see the technician. He's checking the continuity on an entire string, again, using the Dealer 02 along with the long KCC test lead reel. He's got this thing all the way out to the end of the string, although you can't really see it. I'll note here that, the clamp meter, an IR tester, or even a digital multimeter, these can also be used to measure continuity, but not for long runs like this. So this is why we're highlighting the Dealer 02 that gives you that capability for checking long runs. Again, just another photo. Again, you can't see the wire, but it's running all the way out to the end of the string. Again, just checking continuity. See the wire here, it goes out to the end. And just another photo. So next we want to take a look at polarity testing. It's important, obviously, to check for correct polarity for DC circuits, proper terminations. For DC equipment, we're going to measure the voltage on energized circuits prior to closing any disconnects and operating the system. This test should certainly be done on the PV modules, source circuits, output circuits, disconnects, battery and charge controller circuits, inverter input terminations, and any electrical loads, just to confirm the polarity. It's important to check the polarity of every source circuit and the entire PV power source before you connect any DC equipment, because reversing the polarity of an array connection to a battery can lead to serious accidents. It can result in damage to equipment, for sure, and worse, injury to personnel. So really, we just want to test any piece of equipment that's connected to the PV arrangement for polarity. The equipment we would use for checking this is a clamp meter. Here we're showing the DCM 1500S, a safe and convenient way to perform the test. Some of the tests can actually be done without taking the panels out of service, so that's can reduce the risk of shock. Just a couple of features of the DCM 1500S. It's got a Bluetooth connection, so you're able to stream measured values in real time using the MegaLink app that's free, comes with it to a smartphone or a tablet. This allows you to store results, of course, and you can also monitor and record live measurements, all while keeping a safe distance from any arc fault hazards. Again, just a few more features on this, important to point out. The DCM, it meets the requirements of IEC 61010 for Cat 3 1000 volt and Cat 4 600 volt applications. This unit is able to measure voltages up to 1500 volts AC and up to 2000 volts DC. Obviously, this is important. This covers the whole range in a solar field. And then it's got the ability to measure currents up to 1500 amps, both AC and DC. And one of the nice things, it comes with a number of test leads that come with it, including an MC4 plug. So you're able to do direct voltage measurements from solar panels and get a good connection there. And of course, it comes with standard test leads as well. And then it's got a temperature function as well. It's got a thermocouple and allows you to take temperature readings. Just a couple of the features. So here we have a technician. He's checking voltages and polarity on a string in a combiner box. And the tech is, you can see here, is connecting the test leads to the fuse holder. Here. So the DCM will indicate if the polarity is negative or reversed by displaying a minus symbol. I just want to note here, it's important that this photo, the DCM is clamped around these wires, but that's only for convenience. It's not actually measuring anything in this case. He just put it there because it makes it easier for him to freeze his hands up so he can make his connections here and here. So here we have the connection being made directly to the cable. The cable's been disconnected from the fuse in the combiner box. You can see the connections here. Hopefully you can see that. This testing can be done also prior to connecting to the combiner box. And here, just a quick note, this is just showing the DCM being used to measure temperature. So if temperature compensation is needed, you can use this DCM thermocouple. You can see he's got it connected here to the panel. So next we'll take a look at voltage and current testing. We'll look at open circuit voltage testing and short circuit current testing. Again, just need to verify that the PV array and the system are operating within specifications, equipment specs and commissioning specs. We want to verify AC voltage and phasing at the utility supply, the inverter, AC terminals and disconnects, and also test DC voltage and correct polarity for the PV array source and output circuits. And when it applies, you would also want to check correct polarities on batteries, battery chargers, and controllers. These are just some of the common tests conducted for voltage and current, and we'll look at these in more detail. So open circuit voltage testing. This test is done to prove the correct polarity, PV array source. The open circuit voltage, or VOC, these tests require test equipment that's capable of withstanding AC and DC voltages that are over 600 volts. And then we know that by testing multiple strings, we can look for differences in the voltage values. And we know that they should be within 5% between each PV string in the array. And just a note here that the values are affected by temperature and irradiation at the time of testing. We know that voltages can actually change in the range of about 2.5% for every 10 degrees C change in the temperature. So it's just important to keep in mind, lower voltages can be caused by a number of different issues, including poor array cabling or damaged PV module or even bypass diodes. So in open circuit voltage testing, to continue here, to identify faulty strings, you want to verify the open voltage of all the strings. And this is done, what we'll do is divide the voltage of one of the good strings by the number of modules that are in series. And this is going to give us a module voltage. So just for example, if we have a VOC of 500 volts, we have 10 modules in series. So the VOC per module would be 500 volts divided by the 10 modules, and this will give us 50 volts DC per module. So we know that modules in most PV source circuits are in series. So we know that the earth fault location can be based on the voltage of the faulted string. So just for example, if we're measuring on a faulted string, VOCF, that's the faulted open circuit voltage. If that's 400 volts, and we divide it by 50 volts per module, that gives us 8 modules. So the fault location may be 8 modules back from the high voltage or the output side of the string. And next, we'll take a look at short circuit current testing. So this test is done on a PV string, source circuits to confirm correct operation of the system, of course. The short circuit current, or ISC, this requires a test set that will withstand DC currents of over 10 amps. And then you'll also need shorting devices that are suitable for doing the test safely. The short circuit current of a PV array is proportional to the solar irradiance on the system. So we know that, doing this test ideally should be done briefly under clear skies. You want the PV modules to be free of dust or shade. And testing multiple strings, again, we can take a look for differences there. Should show acceptable differences. Again, they should be within 5% between each PV string in the array. So here we have a technician doing some troubleshooting. He's reading voltage. He's connected directly to the cable using the MC4 connectors. You see him here. And again, just using the clamp here for convenience only. He's not actually doing a reading there. It's just a convenient way of putting that up there. He can hang it there while he's making his connections here. Here we have troubleshooting. This is actually where the tech is reading the current. And in this case, he's using the clamp meter. You can see it's clamped around this conductor. And he's reading his current here. Here we show a technician. He's checking current on a cable at a combiner box. And in this case, he's checking current on the inverter side. See his connection here. Again, just to mention this Bluetooth feature. You see the smartphone is set up here. Readings are coming up. Allows remote storage, and you can monitor and record live measurements. Again, all this at a distance for extra safety. This slide just shows some of the screens that are available. This first one showing the voltage, current, and also the temperature. So again, this thing allows connection of instruments to about 33 feet away from the unit under test or live connection. So this is ideal for safe measurements when high rated currents or voltages are present. Has the ability to connect from 1 to 4 instruments at the same time. It's also able to monitor and store live data from up to 4 instruments at the same time and recording individual records. And this is great for comparing differences, different performance elements like voltages, current, temperatures from different parts of the PV site. And then these records can then be managed. They can be interpreted and shared to a central management station or site manager or whoever the asset manager is for that. And they can do additional evaluation, and it's good for record keeping and certainly for future reference in any decision making. Now we're going to move on to insulation resistance, or IR testing. This test helps us identify any faults, PV array and system circuits, and it's really looking at any degradation in the wiring insulation. So we want to determine the integrity of the cabling and equipment. So we know, when a plant's electrical system and equipment are new, the insulation should be in top shape, right? We should see a high resistance reading in those cases. But we know there are things that affect the integrity of the insulation over time. So insulation can deteriorate, and this is certainly many different causes for this. Electrical stress, pinholes and cracks can develop. Moisture can get in then to those pinholes or cracks, and moisture, foreign matter, et cetera, can penetrate the surface of the insulation, and that's going to give you a lower resistance reading and also provide a low resistance path for leakage current, something we do not want. Sometimes the drop in resistance is sudden, like when a piece of equipment is flooded it's very obvious that the insulation resistance has dropped, but normally resistance drops gradually over time. So this gives you some warning if you check it periodically. So again, trending is really important in IR testing. You want to take a look at the readings from the previous test and compare them. If you start to see a drop in the insulation resistance value, you know that that's something you might want to investigate further. And again, with preventive maintenance, it's catching those things before the insulation fails completely. And that's part of the value of doing IR testing. This testing is done, it applies a constant voltage to a conductor and then measures the current flow between de-energized system conductors or between a conductor and earth. And again, a conductor that has good insulating qualities, it's going to measure a high resistance value. We know that leakage currents, it can increase the risk of electrical shock and certainly damage to the system. That's just some of the reasons for doing this test. So any improper deteriorated installations, again, I mentioned earlier some environmental factors, sunlight, moisture, nesting animals, etc. These are common reasons for deterioration of the insulation. Test voltages applied range from 50 volts up to 5,000 volts DC. So all circuits have to be isolated from each other for testing and discharged before and after you do the test. Grounding or bonding connections should be left connected, while any surge suppression equipment, etc., that should be removed from the circuits. And then we need to make sure we have a reliable electrical and mechanical contact from the test leads to whatever is being tested. And some connections might require you to do some grinding or filing if there's contamination, dirt, or even paint on the surface. So make sure you have a good connection. So again, with IR testing, it's carried out in two ways per IEC 62446. You want to check between the positive DC conductor and earth, and then again between the negative conductor and earth. And then between the shorted positive and negative DC conductors, short them together, and then test between those conductors and earth. And this is where I mentioned earlier, suitable shorting devices may be necessary to do this test safely. So anywhere you have modules or structures that aren't provided with metallic support structures or frames with a bonded connection to earth, the test should be done then between array cables and earth, and between array cables and frame to earth. And again, IR testing, it's important to document the readings and look for trends over time. We know that, again, that insulation typically will degrade over a period of time. So trending is important, and catching something early is the goal. And this is just to highlight the IEC 62446. It tells us that any PV system with an operating voltage higher than 120 volts, an IR or insulation resistance value of 1 mega ohm or higher is considered acceptable. And then for PV systems with voltages lower than 120, an IR value of 0.5 mega ohms or higher is considered acceptable. And you see the chart here is for PV arrays up to 10 kWp. kWp, of course, is kilowatt peak. This is the peak power output of a system. So what equipment do we use for doing insulation resistance tests? We mentioned here the MIT 430 and the MIT 2500. We'll be highlighting the MIT 2500. One of the reasons for that is that it goes all the way up to 2500 volts DC test voltage. And again, just going back to the, most handheld units only go up to 1 kV. This is a handheld unit that goes all the way up to 2500. And of course, this is important, as we mentioned, that systems now are up to 1500 volts. So that 1000 volt test voltage is no longer good enough. So I need to move up to a higher test voltage. And again, what this does is we're checking the integrity of the insulation. This unit has the ability to read up to 200 gigaohms. And again, it allows testing to be done per the IEC 62446 testing compliance. So here we have a photo showing a technician. He's doing an IR test in a combiner box. You see the red lead here is connected to the positive conductor. The black lead inside here, if you can see it inside the panel, top center of your screen, that's connected to the ground. And then we see a blue lead connected here to a piece of copper that's wrapped around the outside of the insulation. Now, I just want to note the guard circuit, this unit comes with a guard circuit. And you don't have to use the guard circuit to perform an IR test, but it's important to know that you can use this when you come across, we know that insulation can be covered in dirt. It can be covered with grease, all kinds of external things that can be dirt and contamination on the surface of the insulation. So that can affect your actual IR reading if you have a lot of contamination on the outside of the insulation. So the reading you get is not going to be accurate if there's a lot of leakage on the surface. So what this guard circuit allows you to do is it removes any of that leakage that's caused by the outside, like contamination on the outside of the insulation, and it'll remove it from the reading. And therefore you'll get a much more accurate reading, a much better idea of the actual integrity of that insulation. So again, guard circuit can be used in areas where there's dirt, oil, grease, anything that could provide a path on the outside of the insulation. So if you see readings that aren't very good and you notice that there's contamination on the outside of the insulation, you can try using the guard circuit and see if your readings improve. So next we'll take a look at earth leakage current testing. This is done where live and neutral conductors are accessible and at connected equipment. It's done using the clamp meter, the DCM 1500 that we mentioned earlier. It's clamped around the line and the neutral conductors. So this will measure the difference between the line and neutral currents, and that will give you your earth leakage current. Again, environmental conditions and the type of cabling used in the system, they can affect the performance of the device and the measurements during the test. And then testing separate PV system arrays can help identify earth leakage problems. So this photo shows a technician, he's testing for earth leakage current, and you'll note here that he's connected around, the clamp is actually around both conductors. Here again, just testing for earth leakage current, and you'll note the clamp is around one conductor, and this is done just to confirm consistency of the reading. So now we'll talk about some additional tests that can be done in addition to these 6 typically done tests. And one of them is earth or ground system testing. And this is to test, we need to verify that there's a low resistance of the ground system. Again, these ground systems have to be able to carry any fault currents to the ground to avoid damage to equipment and certainly any damage to personnel. So a ground system, again, needs to have a low enough resistance to carry any fault current safely to ground. The question we get a lot is what's an acceptable value? And typically 25 ohms or less is considered acceptable, but you really need to check local guidelines to determine acceptable values for your system. That's important to check. We do get calls a lot asking whether the readings are good, and again, check with your local guidelines, determine that. But in general, 25 ohms is considered acceptable. So we certainly don't have time today to go into detail on all the ground testing methods, but we did want to mention the follow potential method. And this method is approved or recognized by IEEE 81. It's a basis of the recognized method, IEEE 81. And with the follow potential test, what we're doing is taking a series of resistance readings at various distances between the electrode that's under test, which is represented here in this diagram. And then we're taking a series of readings all the way out to a current probe, which is placed at some distance away from the electrode under test. And of course, the larger your system, the further the distance. And what we know from many tests, this follow potential test has been being done for many, many decades. So what they discovered is when you start taking these readings, you'll see an increase in the resistance readings as you approach here, and you should see a flattening out of the resistance readings. Right around 62% of the distance between the electrode under test and your current probe, that's going to be your true resistance value. And again, you should start to see an increase in the readings as you get closer to the current probe. So again, correct resistance usually obtained at about 62% of the distance from the center of the earth electrode that you're testing to the current probe. And again, this is the true follow potential method, and it's the basis of the IEEE 81 recognized method. If you guys have questions, if anybody has questions on ground testing, you can contact us for additional info. You can also go to the Megger site. We have a number of resources available there, including a booklet that's called Getting Down to Earth. And this goes into quite a bit of detail on ground testing, including theory, test methods, and applications. So equipment to be used for conducting ground testing. That's the DET, the Digital Earth Tester 2/3. Measures, of course, the resistance of the ground system. It's got a number of different test modes. And this model will actually perform every type of ground testing there is, including clamp-on testing. Here's a photo just showing, you can't see the probes that are in the ground, but you can see the connection here to the electrode under test. Again, can't see all the probes heading out, but here they're conducting a ground test on the ground rod here. So some other tests that are done, a radiation examination. So this, we want to take a look at the strike irradiance on PV panels under present conditions, and then these can be compared against the nameplate specifications. And for this, we use the PVM 210, a Radiance Meter. Irradiance, just to note, is it's the radiant flux that's received by a surface per unit area. The international system unit of irradiance is the watt per square meter. So you see that this unit can go all the way up to 1999 watts per square meter. Here's just a photo of a technician using it. See, it's in the same direction as the panel. And then last, we'll take a look at thermographic inspection. So this is for looking for hot spots in the PV panels or in the combiner boxes and distribution panels. And for this, we would use the TC3231 thermal camera. This unit could store up to 6,000 images. It can even set a high and low alarm. Again, this is not so much just a temperature value, but you're looking for hot spots, right? You're looking to compare if there's a spot that's hotter than somewhere else. It can indicate high resistance and heat is generated by that. So these are things you want to look for, certainly in the panels. And just another photo of checking temperature on a panel. Another one from another angle. And here he is checking inside the box. Again, looking for any hot spots, any differences in temperature there that could be a source of a problem. And with that, we'll move on to questions. I'll hand it back to Mr. Fleischer.
All right, thanks, Brian. It looks like we finished up our webinar, our presentation portion of our webinar, and we're going to jump into the Q&A session to answer as many of your questions as we can. So if you have any questions, please feel free to submit them now into the Ask Question box there on your screen. For those of you that are leaving, please feel free to fill out our survey before heading out. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On that survey, there's also a field for you to request a quote or a demo on any Megger products. Additionally, a copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be sent to all attendees within 2 business days. In fact, the link you used to join this session today will turn into a recording link within about an hour after we conclude here. So, one last thing, if you'd like to view other video recordings of previous webinars or register for upcoming webinars, you can visit us at us.megger.com/webinars and register for our next webinar on April 22nd, titled Transformer Protection and Testing Beyond Differential. And it's going to be presented by Sugosh Kuber. So let's jump into our questions. The first one I'm going to send over to Mike. So Mike, can I do IR testing while the system is live?
So thanks for that one, Michael, and for whoever suggested that question. Typically, we don't IR test while the system's live. The recommendations from the panel manufacturers are not to do that. Certainly not while the panels are attached. So if we can isolate the panels and do that kind of testing on cable only, it's usually the preferential way to do that kind of testing.
All right, excellent. Next is over to Felix. Felix, do you need 2 conductors to perform an IR test?
Thank you, Michael, for the question, and thank you for asking this. Yes, so yes, you normally need 2 conductors, so you need at least one as a reference, because you are measuring insulation or testing insulation between 2 conductors or 2 conductive elements. So you need the second conductor to have as a way to compare these values. We have a lot of, as Brian said, application notes and guides that we can share, and we explain more in detail how it works.
Excellent. Throwing back over to Mike, is there typically some sort of DC ground monitor that would detect a percent 2B or conductor being accidentally grounded, at least on the DC side of the system?
So, yeah, that's a great question. I think it was Stephen that asked that one. So typically in our modern day inverters, we have what's called a GFMD ground fault monitoring device. So typically it's set up with a threshold, most of the time somewhere below 32 milliamps. So if the system encounters a ground fault, it breaks the path for leakage current and go ahead and passes the ground fault trip signal to the inverter. So, once that ground fault is gone and rectified, the inverter starts automatically back up. So that's typically what we see today.
Thanks, Mike. Back over to Felix. In your experience, which PV system is more common, ungrounded or grounded systems?
Thank you. So that depends on system configuration and also local regulations. So I understand in the US by the NEC is more frequently used the ungrounded system, but it depends on the configuration. So it could be a roof installation or ground installation, or even in floating systems that are now nowadays more common than before. So the grounding system will be different in a lake, for example, in a floating system. But in the US is most common the ungrounded system.
Thanks, Felix.
Thank you.
And as a reminder to our panel, if you want to make sure we're grabbing the questions we want to answer upcoming, that'd be super helpful. While we're there, I'm going to keep the next question with Felix. When measuring from positive voltage to ground and negative, sorry, let me reread that with the right pacing. When measuring from positive voltage to ground and negative to ground, what can we expect from both an isolated and non-isolated system?
Thank you. Let me just read it again. Okay, yes. So I am assuming this is on an insulation resistance test. If it's not related, please clarify in the chat. So I'm going to answer based on an insulation resistance test. So this is following IEC recommendations. In a healthy system, insulation resistance it should be over 1 mega ohm. That is what we should expect and we should be measuring, as Brian shared in the presentation. So we expect that even if it's positive or negative, it should be over 1 mega ohm if we expect to qualify a system as healthy.
All right. Next question, also sent over to you, Felix. When testing a 1500 VDC PV system, should we test at 2500 volts DC on the MIT 2500?
Thank you. I think this is a current issue in most PV systems. As Brian explained, we are finding now like higher currents and voltages in systems as inverters are growing. So it's in the range of 1,500 volts, and we find up to currents of 1,500 amps as well. So according to, recommendations again from the IEC, the 62446, system voltages over 1,000 volts should be tested at 1,500 volts. So it's 1.5 kilovolts in the voltage that we use in the testing insulation resistance. So, however, there are industrial recommendations or practices depending on the experience of the testing engineer and the system. They can force the system with higher voltages, but the IEC recommendation is 1,500 if you find a system that is working with voltages over 1,000 volts.
Thanks. Next question I'm sending over to Mike. When do we use the guard terminal and why?
That's a great question. Comes up a lot. So, a good rule of thumb is to make at least one reading with and without the guard terminal on every commissioning test, or, if you're out there repairing a system and trying to find inconsistencies with the IR, once again, we're talking IR testing here. The guard terminal doesn't affect the reading after you complete the guard terminal test. Then if the reading's the same as with the guard terminal and without, then we're pretty safe to move forward. I think Brian touched in his presentation on guard terminal usage of that site survey and that visual look at the circuits under test, whether it's through a combiner box or whatever it is, that you see that contamination. We had a couple slides on nesting and those kind of things. So, it's always a good rule of thumb is why not just go ahead and do a guard terminal test on, if you're working out of the combiner box, just go ahead and do one circuit out of the combiner box with and without the guard terminal. But obviously, if we're seeing readings that are very, very low as we're progressing through our commissioning testing, we certainly want to use and incorporate the guard terminal. And if it has no effect, obviously we got a bigger problem that we need to go look at. So, we're the only handheld test device up to 2,500 volts DC that IR tests with a guard terminal. So obviously we have other equipment that has the guard terminal, 5, 10, and 15 kV equipment that has it on there. But it's a great tool for identifying issues that crop up when you're going through your testing, especially in IR testing, where we see readings that are very low, and a lot of readings are within standard, and then we have some that are low. Why not use the guard terminal to identify if there's really some kind of surface leakage contamination that's causing us the problem?
Missed my mute button. Thanks, Mike. I'll send this over to both of you since you're both up here. Is it safe to use the Megger or a Megger equipment on live PV strings?
Yeah, so we have a cutout voltage that's typically 70 volts. So the to protect the operator and the test set, we're going to cut off if the voltage is higher than that. So you're going to know right away when you're doing a test, especially an IR test, if that voltage is of a higher level than we should be looking at doing an IR test. So is it safe? we typically don't want to do IR tests on energized equipment. So that would be the quick answer.
Okay, excellent. Next is over to Felix. Why do voltages from ungrounded conductors to ground often start high and decay towards zero?
Okay, I am assuming that this question is also regarding during an insulation resistance test. If not, please clarify in the chat, please. So that is because the system, once you start running the test, you are loading the system with a voltage, the test voltage. It could be 1,000, over 1,000 or 500, depending on the system, and that behaves as a capacitor. And this is when if you keep applying that voltage, the resistance will change the insulation. Therefore, that voltage will decay. And if it decays very quickly, it's an indication that the system is not healthy. So that is a common behavior on alarms that you can find in inverters. So they will run first an insulation or ground fault alarm system to make sure the system can go live. So I hope I answered the question. If not, please clarification.
Excellent. So next up is still with Felix. Could you elaborate more exactly what is a guard terminal?
Guard terminal. I think it's important, and we use that technology and concept in insulation resistance, not that we use in the electrical infrastructure. So with the guard terminal, which it appears in the tester as a G, which sometimes we tend to assume that is the ground terminal. So we have the positive, the negative, and the guard terminal. So we run an insulation test from positive to negative in our tester, and the guard terminal will measure the leakage current present in that system under test. So any leakage current present in that unit or under test will travel through some contamination or failures of the system or unwanted resistance present in the system. It's very common in isolators, in bushings that we find in substations, and we use the same concept and the same technology in PV systems. If we note that the insulation resistant values are changing, then we will implement the guard terminal to see if there is any issues with the insulation of the cable or the connections between the MC connectors, for example, in strings. We could find also leakage present with the guard terminal.
Thanks, Felix. While I have you, can solar cell degradation affect the system ground resistance over time? I'm sorry, Felix. Did my question come through? Did I miss my mute button again?
No, I missed that. So can you repeat that, please? Sorry.
Oh, so my bad. So can solar cell degradation affect the ground or the system ground resistance over time?
So it could be. So the Brian showed some examples of degradation on PV panels and cells. So if cells can become conductive within the panel, it could bring some serious, let's say, leakage or currents present that will travel throughout ground. So it could be an indication, yes, that there is a ground fault that is originated by the faulty panel, for example. So the conductive paths on PV panels could be in short, maybe because we don't know the reasons, but it could be causes of ground faults in the system. This is why we use especially the camera or other fault finding techniques to identify if there are hot spots that are causing some shortage, like shorting some paths to air.
Thanks, Felix. Back over to Mike. Is it possible to measure earth resistance using a clamp on earth resistance tester?
That's a good question. It is, but we have to keep in mind when we're using a clamp on, it can't just be one electrode out in the middle of nowhere. We use the fall of potential method of ground testing with 3 probes for that kind of testing. But if we have, if you picture pole to pole, transformer to transformer grounds, and they have a parallel path back to earth, that's a good chance that you're going to be okay to use a clamp on earth tester.
Thanks, Mike. Additionally, Gabriel asked, I'd like to ask about ground checks in a grid that is connected to the utility ground grid, and you cannot separate that without cutting the wires. Could you comment a little bit on that?
Well, that's a great question, and we get it a lot. So this is why years ago we created the ART method, commonly used welded, thermal welded type grounding systems where you can. We haven't seen mechanical connections hopefully in a long time, so you can't separate that welded connection. So you have to use the ART method. Attach rod technique is what ART stands for. So we actually use our current probe with the ground tester, and we could be doing a 3 or 4 pole test, but we attach the ground clamp to the conductor, going into a building or into that utility attachment, and we're only measuring the ground electrode itself going into the ground. So this is a great use of the ART technique, and that's a great question, Gabriella. Thank you.
Yeah, thank you. I think we'll come up on our last question here. I'll direct over to Felix. On a DC system with multiple circuits, if you get a ground fault on one of the circuits, would you be able to identify which circuit has that ground fault with the DC amp meter, and how would you be able to tell?
So I don't think that is an easy answer, but yes, you can find, and you need. This is where you need to run a set of techniques to identify the root cause of this fault. But in essence, you might be able to check currents in a combiner box to see what is present or what is missing, what has changed in the system. And then some other common practices is just run through with the clamp in the strings, just checking contacts and connections is what we find in the field, just running through with the clamp alongside the connections. But it's, you can do it, yes, depending on the approach of the engineers on site, but you can start from a combiner box to verify if which string is out of the system.
Thanks, Felix. I think with that, we're going to wrap up our Q&A session as we approach the top of the hour here today. We apologize if we didn't get your question live, but we'll be working to answer any questions we left offline with you guys. So please keep an eye out on your inboxes. We'll be using the email that you registered with as a point of contact. If you'd like to reach out to us to have a more immediate response or have any other offline discussions with us, please feel free to fill out that contact us offline box there on the top right, or drop an email to broadcast@megger.com. We'll make sure we have someone reach out to you with some answers and help give some attention to questions that they deserve. But as a reminder, I'd like to tell everyone we do have a copy of this presentation, a certificate of attendance, and a link to the video recording upcoming to all attendees here in 2 business days, if not before. But I'd like to thank you all for attending. If we could, as we conclude here, I'd like to ask you guys to answer our survey. It really helps us know how we did and how we can improve going forward with future webinars. On that survey, there's also a field for you to request a quote or a demo on any Megger products, request training. But once again, I'd like to thank you all for attending, and I hope you'll have a great week. Thanks for our panelists for jumping on. our presenter, Brian, for taking some time out of his day to do this for us. I know we all appreciate it. But with that, I'll say goodbye and have a great one.
Thank you.